Good. We'll see what happens. Orbital orientations. So within our orbitals, we have three different types, S, P, and D, that we are primarily concerned about. Our S are our spheres. Our P are our dumbbell shape. And our D are our cloverleaf shape. Right? The cloverleaf doesn't hold as a perfect orientation, right? Because we end up with the weird donut dumbbell at the end. But largely what we're talking about when we're talking about these orbital types is that there's different orientations. So for the S-type orbital, there's only one orientation, which means there's only one orbital. For the P-type orbital, there are three orientations, which means there's three orbitals. Since each orientation can hold 2 electrons, you get 6 total electrons in the P type. Okay? The D type, as that cloverleaf, has 5 different orientations. Each of those orientations counts as an orbital, which means you can put in 10 total electrons. Okay? That's what's going on within those orientations and those systems. If we were to, so we're going to ask this question. We want the electron configurations for scandium, phosphorus, and sulfur. So if we were asked that as a question, right, we might need to use the periodic table. Right? Arguably, we would need to use the periodic table. So the first question we would have to ask ourselves is, what are the atomic symbols for each of those? Scandium is a C, phosphorus, P, sulfur, S. Right? Once we have those symbols, we could then use the periodic table to actually give us the electron configurations. Or we could use the electron filling, not diagram, but the electron orbitals that were presented last week that we moved through. So when we're placing electrons into orbitals, they have the discrete energies, okay, which is why we have our atomic line spectrum. So if we were to go through and say, look at scandium we said was Sc, which has how many electrons? 21. Each of these lines represents a single orbital. Each orbital can hold 2 electrons. So if I'm going to look at scandium getting up to 21 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. What the heck? Oh, man. Yep. Damn it. 1, 2, 3, 4, 5, 6, 7, right? When we get up to scandium, and here's where it becomes interesting, because we got 18, where do we put our next electron? 4D. We might say 3D. It turns out that we don't go into the 3D, we go into the 4S first, and then we go into the 3D. Okay? And that might be odd, because you go, well, shouldn't we fill by energies? Well, as we went up, is there a clear difference in energy between the 1 and the 2?
Yes.
Between the 2S and the 2P?
Yes.
Same energy level, but at least in our diagram we can see there's a difference there, right? So there is one. 3S to 3P. Yeah? 3P to 3D. 3P to 4S. Is there a difference between the 4S and the 3D?
Yes.
Yeah, but it is very, very, very subtle. Okay? It is so subtle that another feature comes into play. Not just energy levels, but symmetry. Okay, what do we mean by symmetry? That's the configuration that we would generate first. Okay, we end up with one orbital that is half filled. If we'd filled 3D first, we end up with 3 orbitals that are half filled. Okay? There's more imbalance in that than if we went back to that. Okay? That's a tricky concept to deal with. What we're referencing is a filling pattern, and symmetry has a role in that filling pattern. When does it show up? Right about there. Okay? Where's the majority of the questions that you're going to see on an exam? filling everything below there, because that's a weird exception. Okay, and it's not really an exception, it's following a different rule set, or a new rule set comes into play. All right? So you could go through and reference and say, well, we have jails, and in jails, there's bad people, right? So all people in jails are bad people. No, there's a large variety of bad in jail. You've got people that are thrown in jail because 3 strikes selling pot, right next to someone that's killed 5 people. Those kind of different. Okay? So there's nuances within those bulk categories. Those nuances do show up in our energy filling diagrams, okay? And that requires a little bit more digging into. Okay? That process of filling is actually already on the periodic table. Okay? If we moved through and filled this up to the 3p, we're adding electrons in each time. We started at the 1s. 1 electron in would be hydrogen. First energy level, it's in the first 2 rows or first 2 columns. That's called the S block. So it's a 1s. Helium, also 1s. First row, helium's a little bit weird with where its placement is, so we can float that off. Let's look at lithium. It's in the second energy level, so it's a 2. It's in those first 2 columns, which makes it an S. Okay? Beryllium, second energy level, it's within those first 2 columns, still S. Okay? The next one, we move to boron. Still second energy level, 2, but now it's not in those first 2 columns. It's separated away from the first 2 columns, right? We have this giant white space, visual design element telling us that boron is different than the beryllium. How is it different? Boron is now filling a different orbital type. What's that orbital type? It's the p type. Okay? We can move to carbon. Second row, second column of the p type. Okay? So we're filling those out. Okay? We fill through neon. After we fill neon, we filled the 2p. So what do we move to? Okay, what comes after neon? Sodium. Which row? Third row. There's the third. It's in those first 2 columns, which is S. Sodium is 3s. The filling pattern is actually verified right off the periodic table. After we fill out 3s, then what do we move to? 3p. So we'd end at argon, right? What comes after argon? After 18, we get 19. 19 is potassium. Potassium is in which row? The 4th row. It's also in that first 2 columns, which makes it S block. After 3p, what do we fill? We fill 4s. The periodic table actually told me to skip the 3d. All right? As we continue across, we'd go potassium, then to calcium. Still 4th row, still part of those first 2 columns. So it's S. Scandium. Now things get a little bit weird. Okay? It gets weird because that's not in the first 2 columns. If we look at the shape on this particular periodic table, it looks continuous, right? But if we separate those first 2 columns off and those last 6 off, scandium through zinc are their own section of the table. Okay? Because they're their own section, they are their own orbital type.
3.
What orbital type would they be? 3 is an energy level, so no. What orbital type? D. We covered S, we covered P, there's D. What energy level should it be? This becomes the trick. It's in the 4th row, so we might say 4, except it's the 3D. It is offset by 1. Why the offset? If I place scandium in the 3rd energy level, it would go 12 to 21. I don't know about you, but that's not how we count. My son kind of counts that way. It's not the proper way to count. Right? Because after 12 comes 13. Okay, so maybe scandium should be placed after the P's over here, but then it would go 18 to 21, which is also not the way we count. Okay, so the periodic table has that order and how we fill embedded in it. There are some tricks to offsetting things. The d orbitals are offset by 1 because of that odd fill pattern. The f orbitals, which get inserted here, are now offset by 2. They're offset by 1 because of the d orbitals, and they'll be offset again by 1 because of the fill pattern for the f orbitals. Okay? That's trickier to see. Okay? At least on the periodic table, because you have to fill out a whole bunch of stuff to see that. Okay? Also, those should be embedded in the periodic table, not pulled out. Okay? Why would we have pulled them out instead of leaving them in there? Visual design. It would just be way too long. So we kind of squared it a little bit to make the structure of our image look a little bit squarer. It looks a little bit better. Okay? It removes some information. How important is that information? Well, how often are we going to use these elements? Never. Okay? Well, if we aren't going to use them, we could effectively delete them and not worry about it. Okay? For a general chemistry course. If we were going to advance to nuclear physics or nuclear chemistry, then yes, those become important. Most people aren't going to do that. That's why we have decided as a class of chemists, sorry nuclear physicists, we're just going to pull that out and kind of pretend it doesn't exist. And we'll only worry about the other stuff. Okay? So those offsets and those fill patterns come from the electron configurations. The nuances behind those patterns are a symmetry argument that is really hard to grasp and understand. So instead, it typically gets taught as an exception. Okay? It's not an exception. It's a new rule that comes in or a new pattern that comes in. Bad people go to jail. That doesn't mean all people in jail have the same level of badness. It's a horrible analogy, but it works.
But that everyone's guilty.
Okay? See, I'm a bad person. I used a bad analogy, right? That doesn't mean I should go to jail, for the record. At least not for that. So, orbital capacities. When we look at the first energy level, we get one sublevel, one type. Okay, so there's only one orbit for the first energy level. How many electrons can I fit into one orbit? 2, so I get 2 electrons. How many electrons fit in that energy level? Still 2. Okay? What happens if I move to the second energy level? How many sublevels, how many types of orbitals do I get? 2. Okay? I would get the S type and the P type. I can't refer to it as just an S because then it could get confused with the first one, right? So that's why I call it 2S. I'm referencing the energy level with which it came in. For the 2S, how many different orientations are there?
2, 4,
1. The S type only gets one orientation. It's a sphere, which means there's only one orbital, which means how many electrons? 2. Okay. When we move to the P type, how many orientations are there? 3, which means there's 3 orbitals. Each orbital holds 2 electrons, which means for the P type, I get 6 electrons. How many electrons fit in the second energy level? 8. It's the combination of both of those. Kind of makes sense? Okay. That was fast. Okay. That was.
I'm still kind of confused.
Okay. So, kind of confused, so let's try it again. Because there's the third energy level. Okay. For the third energy level, what types of orbitals are possible? S, P, and D. I have to be more clear because S could be 2S, 1S, 4S, 6S. I need to be extra clear. 3S. What P?
3.
What D? 3. Okay, the S is just a sphere. There's only one way you can orient that sphere in a unique system, which means there's one orbital. Each orbital holds 2 electrons. For the P type, it's that dumbbell shape. Okay, I can do a normal bicep curl, I can do a hammer curl, or I could just grab it by the head of the weight and just kind of do that, right? Everybody get that idea?
Yeah.
Right. There, there. Like that. We don't do hammer that one, right? That's just silly. Okay? But there's multiple ways that we could orient it. That's what we're referencing with the p-type. So there's 3 possible orientations. Each of those orientations counts as an orbital. How many electrons fit in an orbital? 2, which means 6 electrons total in the 3p. When we get to the 3d, that's the cloverleaf shape. There are 5 orientations for that. Okay? Each of those orientations counts as an orbital. Each orbital holds 2 electrons. 5 orientations times 2 electrons gets you 10. So you could go through and memorize those numbers and those sequences. Okay? We started to allude to this on the periodic table itself. Those first 2 columns are typically referred to as the S block. Those first how many columns?
2.
How many electrons fit in the S? 2. These last 6 columns are typically referred to as the P block. Those last how many? 6 columns. How many electrons fit in the p-type? Okay. Scandium to zinc. Those 10 columns are typically known as the D block. How many electrons fit in the D block? 10. Okay, we didn't cover F, but these ones down here are F. Remember, lanthanide and actin, or I never remember L. Those 2 are inserted up here, so we'll ignore those first 2. Okay, that is our F block. How many columns in our F block? There are 14, which means how many orientations are possible for the F? 7 orientations. Okay? So all of that information is stashed on the periodic table. You have to be able to decode that information. Okay? Chemists have encoded it. You have to be able to learn that coding system so that you can decode it. It's effectively going back to the cryptograms. How is that information stored? Okay? So, you can memorize or you can pull from the periodic table. You will also see people draw this stupid diagram. I used to think it was genius until I tried to draw it on an exam and realized that I don't draw things in perfect grid patterns. If you don't draw on a perfect grid pattern, these start to get skewed, which then means your ability to stitch through it to figure out your pattern falls to crap. Okay? But this is showing that same thing. 1s is followed by 2s, followed by 2p, 3s, followed by 3p, 4s, followed by 3d. Okay? The pattern is there. It's also on the periodic table. I think teaching this is silly because the periodic table actually gives you that information more effectively than trying to draw out another pattern. Okay? But whichever helps you get that sequence down is up to you. Yes?
So you're trying to write the
Electron configurations?
Yeah.
Yep.
Do you write the 4s before the 3d on the electronic, or do you write the
Yep.
3d then the 4s?
4s first, then 3d.
Then have it wrong then.
Okay? So I asked you to do a couple things. We asked for scandium, phosphorus, and sulfur. We did scandium a little while ago, okay, where we filled it out individually all the way out. So it was 1s, 2s, 2s, 2p. Sorry, let's try that again. And for those of you being, this is going to look really tedious. Yes, it does. It's to prove a point. 2p, 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 3s, 3s, 3p, 1, 3, 4, 5, 6. I see the hand. Give me a second. Oh, I'm actually going to run out of space. 4s. Fit it. 3D. We've now accounted for every single one of those electrons. In that diagram that we went through and did, that's what we did. We specified the location for each and every one. Could I condense that?
Yes.
Yeah. Okay? 1s2, because it was done twice. What does that 2 represent? The number of electrons that went in. 2s2. 2p 3s2, yeah? Mm-hmm. 3p6, 4s2, 3d1, yeah?
Do we need to write the one?
Okay. Do we need to write that 3d1? I see what you're saying with that. Could I just write 3d? Okay. We should be specifying the 3d1 because it goes back to the meaning of that superscript. What does that superscript mean? The number of electrons. If you don't write the 1, it could be implied that there is one. Okay. But if I now want to check and verify that I found scandium, what could I do? Add all those superscripts. If I don't write the 1, what are the odds I'm going to miss it?
Pretty high.
Okay, pretty high. So if we include that 1, it helps clarify it. The default is to always show your number. Okay? So if we add all those superscripts, we will get 21 for scandium. Fantastic. Okay? Was there a faster way to do this? Particularly because you've got a multiple choice exam and you want to go through as fast as possible. Yes. Where is scandium located on the periodic table?
Third column, fourth row down.
So third column, fourth row, but now let's think about how we would label things according to chemistry. In that third row, we don't want to call it third row anymore because that row is referencing the number of electrons and, in particular, which block it is in. Scandium is in the D block. Okay, it is the first one in the D block, so I could call that D1. It is in the fourth row, so I might say 4D, except I have to remember the D block is offset, so it's not 4D, it is 3D. What happens to all of the orbitals before it? They get completely filled. Okay? They are all filled. Okay? So on a multiple choice test, the very first place I want to look is that last freaking electron. Was that last electron placed correctly? If it was, that's a possible answer. What if it's not? What if it said 4D1? I don't have to look at anything else in that answer. It's wrong. Cross it off. Does that make sense? So you can simplify the amount of work that you have to go through and do to evaluate it. That outermost electron is the most important one as far as our electron configuration goes. The rest will all get filled in. If you see multiple answers that end with 3D1, now what are you going to have to do? Now you're going to have to dig through the weeds and look at the rest of those. How many should you see for an S? How many should you see for an S? How many should you see for a P? How many should you see for an S? 6. Okay? So if you know those patterns, it's now just, well, I'm going to backfill the crap out of it. Okay? The odds that we make you dig in the weeds right now for Chem 130, pretty slim. Okay? Our primary focus is out here. Why would I primarily care about the outside? Yes, everything else is filled. If you were going to meet someone for the first time, do you rip open their chest to see that they have a beating heart?
No.
No. What do you do?
Shake their hand.
Shake hands. Where's their hand? On the arm, on the outside. The very first thing that interacts between two people is the outside. I argue that's the last thing that interacts. No science of lamb stuff, right? Right? Same thing is going to happen with molecules or atoms. The outermost thing is the first thing to interact. That's the outermost electrons. That's where I want my focus to be because that's the first interaction. I can dig deeper if I need to. If I don't need to, if I don't need to prove that you're not a computer, I'm not going to rip open your chest to see if there's a beating heart. I'm just going to accept it. Okay? If I need to dig deeper, then I will. Okay? And yes, plenty of chemists and physicists have. We don't need to. Okay? So that outermost energy level is of critical importance to us because that's the first thing that interacts. That's our first level of now how we can get atoms to interact with each other. That's cool. That outermost energy level is now referred to as the valence electrons, which is what drives Lewis structure. Okay? It's the most important part. That's the thing I need you to be able to see in an electron configuration. That's where your focus should be, not getting buried down in the weeds of your configuration. So if we went through to look at phosphorus, what's our cheat? What do we look for phosphorus?
Where it is on the periodic table.
Where is P on the periodic table?
On the far 6.
Okay, the far right in which block? That is the P block. That was totally unintentional. I apologize for that. Okay, phosphorus is in the P block. Which column of the P block? The third, so it's going to be P3. Which row? 3. Is that one I have to worry about an offset on? Nope. So I'm looking for 3P3. That gives me information that I can now whittle down multiple choice answers when it comes to electron configurations. The rest are all filled.
Doesn't P have to be 6?
P can fill up to 6.
Okay.
For hydrogen, we filled the 1s. The 1s can hold how many electrons? 2 electrons. Does that mean when I look at hydrogen, it has 2 electrons? No, it has the potential for 2. It has the potential for a whole lot more than 118. Right? Just because it has the potential doesn't mean there's electrons there. The electrons there come from it being identified as a neutral atom.
Are we going to get to the 5s part, or are we going to
Nope.
get to the 4s?
That's where we said 4s, 3d. That's it. That's our line. Okay? You could see questions about 5s, okay, or even 5p, okay, where you're not going to see things drift in is through the middle here. Why could I ask a question about 5? 1, 2, 3, 4, 5. What's the electron configuration for strontium? Which block is it? Which block is it? It's in the S block. Which column of the S block? 2. So S2, which row? 5. 5S2. The rest are full. Okay? So I can still ask questions there because it's not any weird exceptions. I won't ask questions for, say, zirconium because that's now bringing in an exception with the offset of the D block.
Why is P in the 3rd row?
Why is phosphorus in the 3rd row?
Isn't it 4th?
Helium is our 1st row, neon 2nd, argon 3rd. Where is the P? It aligns with our argon. Okay? Which column is it in? 1, 2, 3. So we get 2 3s coming in for phosphorus. Okay? There's the 3 referencing the column. There's the 3 here referencing the row. The P is now referencing which section of the periodic table. Which section of columns do I need to be looking at?
Can we just move helium over when
Yes. And arguably, hydrogen and helium can just float off the top of the periodic table. You could just ignore them. Because when it comes to electron configurations, we probably aren't going to look at helium. We won't look at helium, and hydrogen we rarely look at.
So just to go through the very beginning of like writing it out, we could just.
Yep. Okay. Sulfur. Okay. P block. Which column is sulfur in? The 4th of the P block, so P4. Which row? 3rd, so 3P4. The rest fill.
So rewrite the rest.
So, do you think this would be something that you could show your work for?
No.
Okay. You could write it all out. Is that actually showing work, or is that just writing down that you memorized those placements?
It's just memory.
Memory. So that's not showing work. That's showing that you could regurgitate a bunch of
Numbers.
numbers. Let's go with numbers. That's a better way. Okay? Is that really work?
No.
No. So would I ask this in a show your work? No. This is multiple choice. Do you need to write it all out? No. You need to be able to look at it written all out and be like, that is valid. Okay? There are examples of it in the practice exam. You could look at that to get that feel for what you'd expect. Okay? What we just also addressed was our valence electrons. Our electron configurations give us information about the chemical properties because that tells us where our electrons are. It tells us where the hand is effectively on an individual atom. Okay? It also tells us where every other aspect of that atom is too. The hand is the most important part. That's our valence electrons. That hand is our highest energy level. So when I look at sulfur, this gets a bit interesting. Because if I look at sulfur, what did we say it was? 3P, 4, and then we said the rest was filled. So I'm going to fill in the rest. 2 plus 2 is 4 plus 6 plus 2 plus 4, 16. How many electrons does sulfur have? 16. So it totals up. Okay? Valence electrons, our highest energy level. Said the outermost electrons are the ones we care about, and that's why we were looking here. Valence electrons adds a slight different complexity to this. That complexity is highest energy level. How many valence electrons does sulfur have?
4, 8.
Okay. So one option is to say 4, because there we go. This was our highest energy electrons. There are 4. I did not say highest energy electrons. I said highest energy level. The level is referencing that 3 in front. Is there another third energy level set of electrons? How many electrons are in that one? How many total electrons do I have? 6. So I can pull my valence electrons from the electron configuration. It requires a little bit more digging. Is there another cheat? What is the Roman numeral name of the column where sulfur is located?
6.
VI, right? Which is 6. How many valence electrons did it have? 6. The valence electrons are actually written across the top of your periodic table. Everything in that family has the same valence electrons. Different energies, but the same valence. Okay? So you can pull it directly from the Roman numerals, or if you use the other numbers, for the P block, you'd be subtracting 10. Okay? So for sulfur, it was in the 16, subtract 10, and you get 6. Why are we subtracting 10? Because of the D block with 10 electrons. That numbering part disappears from our system. Yes?
So you get the balance electrons for the middle 10? Or
We don't worry about them. We don't worry about them. So one of the big reasons why we aren't going to worry about the valence electrons for the middle 10 is that where valence electrons are going is towards Lewis structure. And Lewis structure is concerned about covalent bonding. What is a covalent bond?
2 atoms share an electron.
Share an electron. Are those atoms sharing electrons? No.
Damn.
That's an ionic bond. What do you mean?
That's an ionic bond. So your definition of sharing electrons becomes challenging. We need to be able to decide what is sharing versus not sharing of electrons. This is where we break our category of bonding into 2 sections, ionic and covalent. Covalent is officially sharing of electrons. Ionic is not sharing, which is a massive gray area, and we'll talk about that a lot later in the semester. Okay? So ionic is a transfer of electrons. Sodium to chlorine is actually a transfer of electrons. Why is that one ionic, but say carbon to hydrogen covalent? Metal and a nonmetal. So instead of thinking about it as sharing, that is true, but that's a much harder thing to look at an image and say that's what that is without knowing a lot more background behind it. So you can jump to a rule of thumb to classify those compounds because that will help you interpret. So why do I not care about the valence electrons for that entire middle section? That entire middle section is classified as metals. And if they're metals, they're all going to be ionic bonds. I don't care. When we're talking about Lewis structure, we're concerned about the covalent compounds. Okay? Which is kind of skipping around there a little bit. Here's our periodic table, nicely colored out, okay, with those blocks. Those first two columns are our S. The orange in the middle is our 10. Our green ones are our P. Notice the hydrogen and helium are both labeled as red, even though they aren't placed in the same location. That's that same issue with floating hydrogen and helium off the periodic table. If we float them off, it makes a little bit more continuity sense.
Okay, so helium is an S, right?
Helium is an S. Yep. Okay. Atomic radius. We had this question about atomic radius, right? What happened to the radius as we went down a column? It got larger. Why did it get larger?
Because there's more things in the nucleus. More protons and neutrons.
Okay. Why does it get larger? Is it due to the protons, neutrons, or electrons? Electrons. Our protons and neutrons are in the nucleus. If the atom is a football field, the nucleus is a marble inside it. So when we're thinking about atomic radius, it's really the electrons that are the primary drivers of that. So when we go down that column, right, and notice I said primary drivers. When we go down that column, what happens to the radius? It gets bigger. Why?
Because you need more energy levels for the electrons.
We have more electrons at first. Much better to bring in the term energy levels. Okay? What happens as we go left to right to radius? It gets smaller. What happened to the number of electrons? It also went up. Okay? So that would seem to contradict, right? As we go down a column, we'd say more electrons. We go across a row, more electrons, and yet the size doesn't match, right? When we're going down a column, what's changing is not necessarily more electrons, but where those electrons are located. As we go down a column, those electrons are located at higher energy levels, which is what's giving you your difference in radius. Fantastic. What happens to the energy level when you go across a row? It stays the same. The energy level. Answer the question that's asked, not the question you want to answer it. You're answering radius. What happens to the energy level? Lithium is in the second energy. Beryllium's in the second energy. Boron's in the second energy. They're all in the same energy level, which means what would happen to the size of the atom if the electrons go to the same energy level? It should stay the same. They're all going to the same energy level. It's not going further away. It's not going closer. It's going to the same energy level. That's not what we see. What else changes? Now the nucleus comes into play. Because the electrons are going into the same energy level, I don't see a change in shape or size. But the nucleus also gets stronger because there's more protons. If the nucleus gets stronger, what does it do to the electrons? It attracts them a little bit closer. That's why it gets smaller left to right. So common misconceptions on how this is explained. Down a column, more electrons. False. Down a column, the electrons are going into higher energy levels. Left to right, it gets smaller because it's a stronger nucleus. It's only half right. Okay? Because down a column, it's also a stronger nucleus. So left to right, what's happening is the electrons go in at the same energy level and the nucleus gets stronger. It's that piece together. So when you're thinking about nucleus, that's good. It's not the primary driver. This would be the difference on filling 4S versus 3D. We first go to the energy level. There's not much difference in energy level. What contributes to that difference? In that case, it's symmetry. In this case, we're looking at how that nucleus affects it. Okay? So those are your trends with atomic radius. You are expected to be able to predict those. Okay? As trends. The next big concept that comes out, which we'll actually look at its derivation probably in Unit 2, because I don't think we'll have enough time to really actually dig into it, electronegativity. Electronegativity is and if you're looking at the slides, you have to skip like 3 or 4 slides. Electronegativity is the ability for one atom to take bonding electrons from another atom. Okay? So I have to bring two atoms together. They now have a bond. The ability for one atom to take electrons from the other is its electronegativity. Okay? The larger the number of electronegativity, the stronger its ability to pull electrons away. Okay? So when we look at this, it increases up towards the right. All the way to the right, fluorine has the highest, helium is lowest. In fact, it's 0. These are all referencing bonding ability. What can you tell me about the noble gases?
They can't because they're like.
They don't bond. If they don't bond, they can't really have an electronegativity. Okay? So because fluorine forms a bond, it's the last one on our column that forms bonds, it's going to be one we'd evaluate. If we compare that out to the rest of it, you'll notice the trend increases to that upper right-hand corner. Is it perfect? No. Are there weird kind of pseudo-exception things? Yeah. But the trend is there. Okay? And what I would expect you to know is the trend. It increases towards that upper right-hand corner. Okay? One of the things that you won't get asked, which was asked in the play posit for the express purpose of you getting angry and saying, what the hell, how would I answer this question? The questions that you will get asked will rank elements going that direction. You will never see elements ranked going this direction.
Oh yeah, I can get that one.
You can't rank them that direction according to the trend. There's no way that you could sequence them to be able to get the information to say who is more electronegative than the other one. The only way you'd be able to answer the electronegativities right to left is if you have them memorized. That's it.
And we're not gonna do it.
Right? And it's a waste of your effort, so don't do that. Right? What you are expected to be able to do is to know the trends so that you can predict things with what happens when we look at a bond, which is Lewis structure. Okay? Yes?
Wait, so we don't have to know about like how electronegativity works?
We'll see. I doubt it. We've got 20 minutes. I doubt it. Okay. Ionic charges. We get this concept of isoelectronic. Iso meaning equal, electronic referencing electrons. Okay. So what is happening is that you are expected to know certain charges on ionic elements. So when they have formed an ionic bond, you should know their charge. Do you have to know it for all of them? Someone just took a picture. It was a bad idea to take the picture at that point. Do you have to know it for all of them?
No.
No. You only have to know it for the ones that are identified. Notice I subtly just erased tin and lead. Right? And I'm also going to go through and add zinc, cadmium, and silver. My argument is that you only have to memorize 4. Those 4.
What's the silver one now?
What's that?
What's the silver one? Plus 1?
Plus 1.
Okay.
Yeah, that's why I didn't write a number next to it. It's just a plus.
Okay, makes sense.
Okay? Why just those 4? Why not memorize all the others? The term is same electrons.
Because it says by the with the number of the groups. Yeah, the column tells you
The column tells you the charge. So 17 is the same as minus 1.
no.
So Roman numeral 7 is the same as minus 1.
No.
No, okay. What you could go through and do on the test, immediately memorize this, so that now you don't have to memorize it any longer, because it's consistent within that. That's cool. You can add that information to your periodic table, and I'm fine with that. That's actually probably faster than what I'm about to discuss. Isoelectronic, same electrons. Same electrons as what? Think about your current status. What do you think would make you be like, yep, I'd be happy if that happened? Right now. Someone walked in the door. What was that, Ernest? Because you might have just said it.
Money to pay for college.
Money. Someone came in and said, here, your money's paid for college. That's good. Think bigger. Here's $400 billion.
Go down.
You're going to be like, yep.
I'm gonna quit for jam when I have it.
There we go. You can do whatever the hell you want for the rest of your life. You don't have to stress about it. Okay, cool. Okay, who has $400 billion? Okay, Bill Gates. Now rewind back 100, 200 years ago. Who has the equivalent of that?
Rockefeller.
What's that?
Rockefeller.
Royalty.
Further back, royalty, also known as the
Same.
nobility. Noble gases. Everything wants to look like the noble gas. What can fluorine do to look like a noble gas? Okay. If we look at xenon, how many electrons does xenon have?
8.
Try again.
Oh, sorry about that.
54. How many electrons does fluorine have?
9.
9. So fluorine could change its number of protons to look like xenon. But if it changes the number of protons,
Changes the charge.
changes the element, it doesn't exist in it. It's no longer fluorine. So I can't change the number of protons. Neutrons don't contribute to charge, so I'm going to change the electrons. For fluorine to look like xenon, what does it have to do?
Lose an electron.
It is one of them.
To look like xenon, how many electrons does xenon have? 54. If I add 1 electron to fluorine, I look like 54. 10 is the same as 54.
Yes. Your kid says that.
Okay. My kid's also not in college, so no, that doesn't work, right?
So it means
But if it did that, that would be cool. Okay? But that's really hard. Okay? That's like you trying to look like Bezos. Bezos, Amazon dude.
yeah.
Let's just go with that. Okay? That's a really big jump. But could you look like who's someone that's also stupidly wealthy but not that much? A Kardashian. Okay? Could you look like that's probably a little bit easier to do. All you gotta do is make a sex tape, right? And there you go. Okay? What's that level of difficulty? What does neon have? 10 electrons. How does fluorine look like neon? It gains 1 electron. If it gains 1 electron, it would have how many electrons?
10.
What would its charge become?
-1.
-1. Because it has 9 protons.
And it gains a negative.
Okay.
but it doesn't gain-
What does iodine need to do to look like xenon? How many electrons does iodine? Man, that pen is just not staying there. 53. What does iodine have to do to look like xenon? Gain 1 electron, which means it would be -1 charge. Everything's trying to look like a noble gas. Why do we not have you memorize carbon? You don't know. Yes, you do. How many electrons does carbon have? 6. What could carbon do to look like neon? Gain 4 electrons. That's a lot. But I could become positive, right? So instead of gaining 4 electrons, I could lose what to look like helium?
Lose 4.
Which is easier, gain 4 or lose 4?
Lose 4.
Gain 4 or lose 4? It's the same. Which means what happens for carbon? It could be either state. Right? Which is why we don't have you memorize it. The whole point of memorizing it is because it's always that. That's why we memorize. Okay? Simplify the work that you have to go through and do. When we go over to lithium, we can do lithium. Take a look at lithium. What element is it trying to look like? What's the closest noble gas to lithium? Helium. To look like helium, what does lithium have to do? Lose 1 electron. What's the charge on an electron? Negative. If I lose a negative,
You got a plus.
I became positive. That's why lithium is a +1 charge. Okay? Since we're talking about the gain and loss of a negative species, we have to be a little bit careful with our signs in that application. Yes?
I know this doesn't apply, but like what are the charges in the middle ones?
So the charges to the middle ones become vastly more complicated because you're looking at the d orbitals, and those charges oscillate. So for instance, for iron, it has 3 or 4 common ionic charges. Because there's a multiple different amount of charges, you're not required to memorize it. You will be required to specify it in Unit 2.
Wait, so if you make it from the Lewis structures, for like example, like NH
So NH4 minus is a separate issue with Lewis structure. This, unfortunately, seems to segue into Lewis. It doesn't segue into Lewis at all. It's just referencing our common charges. When we segue into Lewis, Chapter 4 summary, by the way, those are all the big important topics. They're in the slides. Chapter 5 summary, big important topics. When we segue into Lewis, you're looking at bonding. They're in the slides. Okay, and I can go back to them later. We've got our ionic bonds, metal and a nonmetal, covalent bonds, two nonmetals. Those are our primary categories. Lewis is focused on covalent bonds. We don't care necessarily about the ionic. Lewis still works there a little bit, but it was built for covalent compounds.
Why don't you make us memorize bond? However you say that in English.
It is +3, but it has some variability. Why do we not make you memorize it? You don't use it.
You don't use it?
Yeah. Okay, we're going to skip that for the moment. There's ionic compounds. They're generating charges, so positive and negative. So when we took our metals that were all positively charged and combined them with our nonmetals that are negatively charged, we now have an ionic compound. Okay? For our covalent compounds, the interaction becomes a lot more complicated, and that's Lewis structure. That's that play posit I asked you to watch. If you have not watched that play posit, according to the grade book, about half the class, you're going to miss 10 to 15% of the questions on the exam on Thursday. Okay, which is fine. You can accept that as a loss, but realize you're losing that right now, okay, if you don't know Lewis structure. These are the rules that I recommend you go through and follow. There are a multitude of different rule sets for Lewis structure. These rules work now in Gen Chem 1 and in OChem. The rule sets that you memorize that other people seem to push and present do not work when you get to OChem. They fail miserably. Okay? If you follow these rules, these will work all the way through your entire chemistry career. Okay?
Skip play posit 0 or
It's 1. Play posit 1.
So I heard two different kind of things today. I have it written in my schedule that the exam is next Tuesday. Oh, it's Thursday.
It's this Thursday.
Okay. I thought I
Yeah,
heard
'cause
Greg
Greg kept
say
saying
it's next
Tuesday.
Yeah.
Maybe he's talking about the English exam? I don't know what he's talking about when he's saying it's next Tuesday, because
We
it's.
show up at the library at 7 and then.
I heard him say
here for-
Thursday.
for the chem exam.
Greg, when's the chem exam?
Thursday.
Don't tell you guys.
What day do we go to the library?
Thursday.
That's what I heard.
Tuesday. You did say
Yeah,
Tuesday.
you're saying Tuesday.
I don't know. I heard Thursday, so I don't know.
I heard Thursday too.
Well, either way, there's going to be an announcement that posts at 9:50 to remind you that Thursday we go to the library at 7, but we have the chem exam at 8:30.
Yeah.
And so at least you guys will be lively, awake. You will have had some cardio just from coming in, get that nervous energy out on the walk over.
I don't know what to tell you there.
I don't think I said Tuesday, but I'm
Yeah.
sorry if I did.
Which is interesting. About half the class heard Tuesday, half the class heard Thursday.
Well, I know in here
So
it says Thursday, so that's what I was wondering. He did say Tuesday.
There, if you look at them just on the screen, like they look very similar.
it's okay.
Anyway.
Shape summary. Okay. I don't think you did anything. The shape summary. The shape summary comes from interpreting the Lewis structure. If you can't interpret a Lewis structure, you can't do shape. That's how it goes. Shape comes from Lewis. You will not have this chart. Okay? Where I would argue you should spend your time is right down here at the bottom. Okay? Most of those are limited applications, so aren't really worth the effort. Down here is your happy place or angry place. Okay, it's up to you. Okay, so Lewis structures. In the play posit, there's a section on formal charge, and yes, you can entirely walk away from it, and it actually looks like, if I did it pseudo correctly, when it says that you could ignore it, you still have to let it play, okay, unfortunately, and you can't skip it, which I thought you could do, but you can't. Okay, you just let it play, walk away, do something else. It'll pop up with a question at the end of that section of formal charge. Answer whatever you want, and it'll start back where you need to be.
It says it's like a reminder. It's ended.
Yeah. so sorry. These are our summary of our rules. CF4 was done in the play posit. Okay, we have a bunch of other things put up there. One of the things I added up there is this new one for carbon. So let's look at a really, really simple Lewis structure. Carbon is a bad one to reference, or any atom is a bad one to reference for Lewis structure. Because what ends up happening is the Lego model of Lewis structure, which is incredibly common, and it's great if you're in elementary school. We're not. Molecules are vastly more complicated than freaking Legos. You can't just mash them together. Okay? There's a pattern behind them. But if we go through and look at it for an atomic structure, we've got carbon. How many valence electrons does carbon have? 4. It has 6 total electrons. 4 valence. We'd find the valence by writing out the electron configuration, which is tedious, or we look at the top, and it's a Roman numeral 4. It has 4 valence electrons.
Wait, it's built into the periodic table?
Yes, sir.
We talked about that already. We now want to place those 4 electrons around that atom. Okay? How it's described in the play posit is we put it in pairs. Why are we talking about putting them in pairs in the play posit? Because we're talking about building a molecule. Is this a molecule? No. Okay? Which is why when we look at the atomic system, all of the rules change. That's because it's the atomic system, not the molecular system. Lewis structure is built for molecules, so looking at an atomic system is dumb. Okay? The textbook does it. I know. The textbook is dumb. Okay? So what we would do would be place those electrons on the faces of a square around that center atom. Why a square? Lewis was based off of cubes. Do you really want to draw a 3-dimensional cube? No? Squish it, you now have a 2-dimensional object, which is a square. There it is. Okay? And that would now be our atomic dot structure for the atom of carbon. Why people tend to like this is that what happens if we moved up to, say, CH4? Well, if CH4, I now have hydrogen, which has how many valence? 1. How many of them are there? There's 4. So I could do hydrogen 1 dot, hydrogen 1 dot, hydrogen 1 dot, hydrogen 1 dot. Yeah? Now where I have a pair of electrons between atoms, I can turn it into a line and go, oh, look, it works. In one freaking circumstance. At best, a handful of circumstances, okay, where it really falls apart is when we try and get into actual applications of where the electrons exist. This model, if we look at molecules and how they work, we're talking about how electrons are shared across atoms. Humans do this too. We share food. At the end of the semester, we'll have a potluck. We all bring food to this potluck, right? Okay. Are you only allowed to eat your food? No. You're like, that's stupid. It's not a potluck. It's not a freaking potluck. Lewis structure is a potluck. We all contribute the electrons to the party. There's now a pool of food. Who gets to go first? This is where civility kind of comes in out the door. Okay? When it comes to Lewis structure, there's a priority of who goes first. Who wants the electrons more? We could do the same thing at a pot. The whole point of potluck is civility, but if we got beyond that part and we stopped being civil, who gets food first? The biggest, strongest, meanest person. There's electronegativity. That's who gets the electrons first. So they will go through the line and they will pull all the food they want. Does the next person get to pull all the exact same food? No, because the biggest, strongest, meanest just stole all the food. Okay? After the food has been distributed, now the biggest, strongest, meanest gets nice again and goes, oh, I'm sorry, you didn't get any food? Here, have some food. You can have some of mine. It's that sharing process that happens when we build a molecule. In the process we just walked through, there is no sharing. It was they each brought in and they all ate their own food. That's crap. That's not how molecules work. Okay? So, let's look at a better example, SO3. Now we'll move straight to a molecule, SO3. We need to know the valence electrons. How many valence electrons does sulfur have? 6. How many valence electrons does oxygen have? How many oxygens are there?
3.
3. Rule is total the valence. What's my total? 24. Now what's the rule? Center atom. The center atom is typically the least electronegative. If you know your electronegativity trends, you would know that S, sulfur, is the least electronegative. It's the middle. We're basing this off of Lewis's model of a square, so we'll place the oxygens on the face of that square. Okay? Now what can I do? Now I can add the electrons. And I'm going to add the electrons to the biggest, meanest, ugly, well, they don't have to be ugly. They could be pretty. Biggest, meanest, prettiest person. Okay? That person is our most electronegative. Which one was our most electronegative? Oxygen. Sulfur was our least electronegative. That's why it went in the middle. Okay? Oxygens are most. I'm going to start placing those electrons in pairs. Why in pairs? The whole goal is to achieve an octet. Why 8 electrons?
Because you want to be in a double.
We're trying to achieve that noble gas configuration. Okay, that full octet. I've now placed 8 electrons around that oxygen. How many do I need to place? 24. So what do I do? Go to the next oxygen. Next oxygen. How many electrons have I placed? 24. Now that I've placed my electrons, I will convert pairs into a line to represent bonds. To have a bond, we must be sharing electrons. So the electrons must be located between 2 atoms. So I can only, I can only draw 3 lines. 1, 2, 3.
Doesn't that false?
Doesn't go.
You can add a little more lines so it falls.
You need enough in the middle.
You take
Right.
2.
If we go through and look at this, that's our rule. Now we move to rule 6 and we satisfy octets by moving pairs. Okay? This is where my method stands out and trumps all other methods. Because what's going to happen with other methods, they go, oh, well, you needed another bond so that we had octets. So that's the answer. That's a third of the answer. Why is it only a third? Those electrons could have come from any of the oxygens. So you would need to draw all 3 as potential answers. That is the concept of resonance. If you just go, well, I need a double bond, you end with one structure, and you're like, well, what the F is resonance? I don't understand why it works. It works because of how we set this up. It works because we get to this point where we've placed the electrons, and we've gone 6 satisfy octets. Are there 8 electrons around each of the oxygens? Are there 8 electrons around the sulfur? No. It is missing a pair of electrons, so what do we need to do? We will now need to give it electrons from a source. Which source? Any of those 3. Which means I have to acknowledge that this is a valid answer. So is this one. And so is this one. Okay, with all our electrons in gory, gory detail.
Do you need us to do that?
If I don't explicitly state, do not draw resonance, then yes, you need to draw that. Okay? Some people will say, well, aren't you just rotating the structure? No, you're not. We're looking at resonance, the structure is pinned. Okay? You've effectively flayed the structure out and it can't move. You're now just changing where the electrons exist within that structure. If you follow the methods proposed elsewhere, you don't get to that process. You just kind of jam until it works. This actually distributes the electrons according to how atoms want those electrons. Lots of hands. We'll start 1, 2, 3.
Can we just put the double bonds on each of the oxygens to make it easier, and then they would all still have...
This?
Yeah.
How many electrons around the sulfur?
Too many.
16. How many electrons are supposed to be around it? 8. So no.
Can I put the oxygen on the left side, or does it have to?
Can you change where the oxygens are located? Yes. That's not going to change anything to do with the molecule or the structure. That's the arbitrary placement on those 3 faces. It doesn't matter.
Doesn't matter.
Nope. Once you've placed one, don't start changing them with each of your resonance structures. Keep it pinned.
So going back to Earth question, what if we just did 3 double bonds? Wouldn't it satisfy it?
Isn't that 3 double bonds in black?
I mean, like you add another line to the oxygen on the right. So you have O2 with 2 lines. Then to the right of the S, you have another O. So one line.
So you're saying for this one? In that structure? I honestly have no idea where you're referencing.
Like, what if you do that? Wouldn't that satisfy it?
What you just drew right there is literally what's in black in that circle.
He's drawing 2 less electrons on the oxygen, I think is.
Okay, so the suggestion is to get rid of those?
No. Like, you just add another line right there. Wouldn't it satisfy it or not?
So right now, the sulfur is wrong. The sulfur is your problem in that structure. The sulfur has more than 8 electrons around it. It doesn't matter if you add more lines. Sulfur is still wrong. If anything, you have to remove lines from the sulfur. Okay? That structure is inherently flawed. You can bring in aspects of formal charge, which is a whole nother can of worms that you do not want to open, particularly before the exam on Thursday. Okay? And that's going to be the other problem. When you go online, they're going to give you the answer. Which answer? The answer for OChem. You're not in OChem. Be careful using the internet with Lewis structure, because you are not expected to go all the way to that level. You're stopping way, way, way early in that process. Yes?
Do you care where we place the electrons? Because you placed it on, when you place the double bond?
Where the electrons go around an atom are the same thing as where the atoms go around the center atom. The exact placement doesn't matter.
Will
Right.
resonance be on the exam?
Resonance is fair game for the exam. Yes.
So make sure you remember that there's more than one way to.
Sorry, Greg, stop. Right here. Big, massive thing that you need to purge for the exam. You get the periodic table. Okay? You are expected to know atomic radius. You're expected to know electronegativity. You're not expected to know ionization energy, so don't worry about it. It will show up on the exam. We're just going to delete those questions. You're also expected to know valence electrons. Right? So when you are told to start, you can flip to the periodic table, draw a bunch of arrows, put it up there. You now have it done. Right? When a question gets asked about those topics, all you've got to do is look down where you wrote the information and you've got your answer. If instead you're like, I can memorize that information, notice the arrows don't all go the same direction. Okay? Which means you can draw different conclusions to different aspects of those names. Okay? It is going to be very easy to confuse those topics and get it inverted. Be careful. Purge stuff that you want for your test first. Once it's been purged, then you can continue the test. Okay? In the 30 seconds that I've got for the next